Okay, our next section is going to be over polar coordinates, and this is basically a different way of designating points in the plane, in a two-dimensional plane. So up to this point, what we've done is we've used rectangular coordinates. And so we've had an X and Y axis, okay, and we have this graph paper, and on our graph paper we have a bunch of rectangles or squares, okay, and we can designate a point. I'll just designate like this point right here, and you need two numbers to designate the location of that point. In this case, this horizontal number, which is the X, is 3, and the vertical number, which is the Y, is 4. So that point is like 3, 4. Okay? We could do another one, like maybe this point over here. So the X coordinate is -5, the Y coordinate is 2. -5, 2. Or maybe this point over here, right? The X coordinate is 4, the Y coordinate is -3. But the point here is that any point in the plane can correspond, or we can correspond an ordered pair to that point. Okay, there's going to be, and that's kind of a location. That's kind of a name for that point that actually designates its location. And if you have a two-dimensional space like this, you actually need two pieces of information to determine the location. So in this case, the horizontal distance, the vertical distance, and then you can pinpoint that point. Okay, but this isn't the only way to designate points in the plane. There are other coordinate systems, and a very useful one, especially when you're dealing with circles and stuff, is something called the polar coordinate system. And this would be what the graph paper would look like for a polar coordinate system. And we don't have squares or rectangles like we do here. We have sectors. Okay, so what this graph paper is made out of is we have these concentric circles kind of radiating from the center, and this center is known as the pole. So this is the pole, P-O-L-E. The center is the pole, and then you have these concentric circles all centered at the pole, radiating outwards. And then you also have angles, these angles measured here. Okay, and like this line is pi over 6, this is pi over 3, pi over 2, 2 pi over 3, 5 pi over 6. So the reason they didn't include the pi over 4 is they wanted these all evenly spaced around the circle. But there's actually, you might not be able to see it, but there's actually a light mark in between each one of these. And that would actually be pi over 12, this would be 3 pi over 12, 5 pi over 12, so on. And the 3 pi over 12 would be the pi over 4. Okay? And so the idea with this is if you have a point, let's say in the plane, I'll say this point right here, okay, we're going to designate this point with two numbers, but one number is going to be the distance that it is from the pole. So this distance, and we're going to call that distance R, kind of an R for the radius of the circle out to that point. Okay, so that R distance is the distance from the pole out to the point. So in this case, it's 1, 2, 3, 4, 5. So my R is 5. Okay, and then the other number is going to be the angle that gives me that point. Okay, in this case, pi over 3. So what I'm doing is I'm designating that point not with an X and a Y coordinate, but with an R and a theta. So this is like X, comma, Y. This is R, comma, theta. So the ordered pairs are an r, which is the distance from the pole, and then the theta is the angle that it is out from, or the angle that it is from this x-axis. So in this case, we have 5 and pi over 3 designating that point. Okay, so any point then can be designated this way. So this here is 3 units out from the pole, and the angle from here to there is 7 pi over 6. So that point would be 7 pi over 6. That would be this point right there. Okay, now the interesting thing here is that there's actually an infinite number of ordered pairs that designate these points, because what I can do here is I could have 5 pi over 3, but I could also go all the way around the circle like that, and then this would be like 7 pi over 3. So I could have 7 pi over 3. Or I could go the negative direction, and that would be 5 pi over 3. And if I did that, and so let me actually write these down. So this ordered pair could be written down with the following ordered pairs. I could do 7 pi over 3. Or I could do negative 5 pi over 3. Okay, so in other words, I'm going the negative direction to get there, and I'm going out 5, and I would get the same point. Or I would go all the way around the circle once and then go there, and that's the 7 pi over 3. Okay, and basically I could rotate as many times as I want and stop there, and I would get another ordered pair for that. So you have all those infinite rotations either direction that could give you that ordered pair. Does that make sense? So there's not a unique ordered pair. But what we're going to say is that this ordered pair is kind of the standard polar coordinate. Okay, there's an infinite number that would give me that point, but we'll say that the one that is between 0 and 2 pi, the positive angle between 0 and 2 pi, is the standard coordinate. Okay? Now there's actually even another way of designating this, and that would be by spinning around to 4 pi over 3 and then actually going backwards 5. So in other words, when I spin around and then I have my terminal side here, this is the positive direction, this is the negative direction. So I could do negative 4 pi over 3, and this would be another ordered pair that would give me this point. So I'd go spin around here, and then I would back up 5. So you can have negative r's, and basically a negative r is going in the reverse direction as the terminal side of the angle. So in other words, if I had negative 5 pi over 3, then I would be going up here, but then I would be going back 5. And so this point down here, this point, you could write that negative 5 pi over 3. Or I could write that positive 5 and 4 pi over 3. So you could, like I say, every point you could come up with a lot of ways of designating that point. But the standard way, the standard ordered pair would be this one. Okay, this one is not the standard ordered pair. So the standard ordered pair would have the angle between 0 and 2 pi, and the r would be positive. So this would be the standard ordered pair. Okay, and I could also designate this by going pi over 6 and then backing up 3. Or I could go 5 pi over 6, or a negative 5 pi over 6 and forward 3. Or negative 11 pi over 6 and back 3. So there's just all kinds of ways that you can designate an ordered pair. Okay, but the standard way has a positive r and an angle between 0 and 2 pi. Okay, that will be the standard way. So that's really kind of interesting, because the coordinate system, the rectangular coordinate system, there's only one ordered pair that designates each point, a unique ordered pair. But here, each point in the plane actually has an infinite number of coordinates because of the way that you can keep rotating, and so that's the idea behind the polar coordinates. So in the next video, what we'll do is we will learn how to convert a polar coordinate into a rectangular coordinate. So given these polar coordinates, how do I find the x, y that would give me the same ordered pair? So like this one would be over here somewhere. How do I get the x, y rectangular coordinate for any of these polar coordinates?